Okay, so today in 6.4 we're going to learn about a new set of coordinates called polar coordinates. And polar coordinates aren't really that hard to understand, especially after you've been doing all of your work with vectors. Polar coordinates are a way to designate a point, and the point is a directed distance from the origin, which means, again, if you think about those words, directed distance, it means it has a direction and a distance. Directed distance, not rocket science. But so if we look at the components, the pieces of polar coordinates that you can understand the vocab, we can kind of go from there. So first off, we have the polar axis right here as labeled in the picture. And the polar axis, as it says in the description, is a ray that goes, from 0. Or from O, from point O, which we term in polar coordinates as the origin. So if you look at the polar graph paper that I placed over on the right, you can see point O would be the origin. Each point has, if you notice, two components, r and theta. R is going to be the distance and theta is going to be the direction. So those two things together give us a direction and a distance from the pole. Okay, let's go ahead and look at like a sample polar coordinate for a moment, and we'll go ahead and graph that. We could say that we have the point, I'll just come up with the point Q, and we'll give Q 3 pi over 4. So as those are polar coordinates, so that means that from the pole I'm going to go 3 units in the direction of pi over 4. And so 3 units in the direction of pi over 4 would be 1, 2, 3, and there would be my point Q. Here we have 3 examples of polar coordinates that we'll go ahead and plot. And so the solutions are here already, obviously. For A, the point 2 pi over 3 goes in the direction pi over 3, 2 units, and there's P. That one's very straightforward, like the example I did on the previous page, but if we look at B, it gets a little interesting. With a directed distance of -1 and a directed angle of 3 pi over 4, we go the direction 3 pi over 4, and then the distance -1 brings us back here, and so our point is actually, even though our direction is 3 pi over 4, we're going back into what would be stereotypically the 4th quadrant. And then here in example C, we have a positive distance of 3, but a negative angle, which means that we now go clockwise instead of counterclockwise, 45 degrees down, 3 units out, and there we are. So here in example 2, we're going to try to find not just one polar coordinate for a point, but we're going to find all of the polar coordinates for a point. Because if you think about the things that we've done with, like, the unit circle, we realize that the concept of coterminal angles can all of a sudden surface here in polar coordinates, because every 2 pi the point will happen again and again and again and again, and so on and so forth. However, there's another thing to look at. So as we take the point 3 pi over 3, and I'm just going to sketch in here. So pi over 3 is going to take us in this direction with direction pi over 3, the distance 3. It happens again 2 pi later, right? So in other words, from here we can go around another 2 pi and it would happen again. So we would write that point as 3 pi over 3 plus 2 pi, which would be another example. So there's another point that has the same, it's the same point with different coordinates. The other way that we could do this, and this is one that gets a little bit trickier, is we could actually look at this. I'm going to sketch down here now, that if I went 4 pi over 3, in other words, I added 1 pi to it, I did, and that's what you see, by the way, right here. When I add 1 pi and I make the direction now, or the directed distance, negative 3 instead of positive 3, we can now move all the way here, which is 1 pi later. This would be 4 pi over 3, and now we move in a negative direction, which means that from here we go backwards, and sure enough we're in the exact same spot, and we have negative 3 4 pi over 3. So the key here is we can either add 2 pi and come all the way full circle, all the way back around again, and that's what's going on over here. Add 2 pi, go all the way full circle, come back around again. Or we can add 1 pi. So here's pi over 3, here's another pi beyond that, but now we change the sign of our directed distance to be negative, and that makes us go back to where the point P is. Now, how we use these two pieces to write pairs for all the polar coordinates are, instead of just adding 2 pi, we will add 2n pi, which would be, where n is an integer. In other words, we could add 2 pi or 4 pi or 6 pi, etc., and go. And that's what you see right here with the 2n pi. Now, the simplification here, I don't know, borderline unnecessary. I think this way actually makes it much clearer as to what's going on. And then same thing here, adding just adding the 1 pi, so pi over 3 plus 2n plus 1 pi, and what this does is when n is 0, you end up adding 1 pi, and then when n is 1, we add 3 pi, and this just keeps it where our pi is always an odd number of pi's. And we need to differentiate between the odd number of pi's and the even number of pi's, because the directed distance is negative for the odd numbers and positive for the even numbers. Okay, so here I've added the equations, if you will, for finding all polar coordinates of a point. The point just becomes r, the directed distance, of course, and then the theta plus 2n pi, or negative r theta plus 2n plus 1 pi. Just as we talked in the examples, but now you actually can see the kind of generic abstract formulas so that you can write those down, put them in your notes so that you have them when you're doing homework. There you go. So here in example 3, we're going to convert from polar coordinates to rectangular coordinates. Now, I think this should make pretty good sense, really. If you look at the formulas for calculating the x and y values of a point right here, okay? When you look at that, what are we really doing? We're taking the cosine value and the sine value, which we know correlate directly to the unit circle, which has a length of 1, and we're going to multiply it by r, the directed distance, which will take that the coordinate that has the length of 1 and scale it out to the proper length. So it should stand to reason that those two things make sense, the r cosine theta and r sine theta. So as we go ahead and start with example A, the point 3 and 5, 6, so we know that x, if I can write, let's try that again. Is going to equal 3 times the cosine of 5 pi over 6, which the cosine of 5 pi over 6 is negative root 3 over 2. So 3 times negative root 3 over 2 is going to be negative 3 root 3 over 2. And the y value will be 3 sine of 5 pi over 6, which is 1/2. So 3 times a half, or 3/2, which means the answer to A is the point negative 3 root 3 over 2 3/2. Wow. Okay, point B would work the same way. So point B, the x will be 2 times the cosine of negative 200, and negative 200 would have the same value as positive 160. Now that one gets a little bit tricky because that is not on the unit circle. So at that point we can approximate using a calculator and simply do 2 times the cosine of negative 200 or of positive 160. Doing that with my calculator, we get the x value equals negative 1.88, and the y value will be 2 times the sine which should be about 0.68. So point B is negative 1.88, 0.68. That's all we have to do. So here in example 4, we're going to now go the other direction and convert the rectangular coordinates into polar coordinates. Now, there's a couple of different kind of ways that you can do this. You might already think, I got it, no problem. And you might be right. We know enough to do this a couple different ways, but I'm going to show you dealing with the formulas that we looked at on a couple pages ago, dealing with those, kind of a, I guess, a new way of looking at this. So first off, one of the things that we looked at on the other page had a formula that we didn't use then, but we're going to use now, that said the following. Said that r squared equaled x squared plus y squared. And with the point P, that means that r squared is going to equal negative 1 squared plus 1 squared, which equals 2, which means r is going to equal plus or minus the square root of 2. Okay. Knowing that we've got r equaling plus or minus the square root of 2 is a great start. We have our directed distance. We need to come up with the directed angle. And to do that, another piece of information on that page was that the tangent of our angle equaled y over x. Now again, not new information. We've known that for a long time. So what we'll do there is go ahead and substitute in, and we find out that tangent of theta equals 1 over negative 1, which means the tangent of theta equals negative 1, and therefore the inverse tangent of negative 1 equals theta. Now, where is tangent negative 1? That's going to be at three pi over 4 or 7 pi over 4 either one. Okay, so I've added the graph of these two things, and you'll notice right away that when dealing with the polar coordinates, what we often do, rather than deal with 3 pi over 4 and then keep going all the way to 7 pi over 4, is actually use the negative angle. So we could take the 7 pi over 4 and instead use negative pi over 4, which is what you see them doing right here. Now, keep in mind, if we do the 7 pi over 4 or the negative pi over 4, either way, we now need to make sure that we're using the negative square root 2 for our directed distance. So, our two answers for this would be negative root 2 and negative pi over 4, and positive root 2 and 3 pi over 4. So those two things would be our answers. So now we do part B in the equation, which is much simpler. I guess first off we can go ahead and get rid of that object, and when we look at part B, we realize that negative 3, 0 is going to have a distance of 3. And again, if we did the whole, x squared plus y squared equals r squared, then r is going to be plus or minus 3, which is important to note because as we think about our issue, we can either go this direction 3 units, or we could go, or we could go and stay right here at 0, but then go negative 3 units. So those would be our two options, and sure enough, that's exactly what we need to do. We simply have 0, whoops, let me kind of wrote that backwards. We have negative 3 units and 0 radians, or we have 3 units and pi radians. And those would be the two answers to part B. So you can see that it's much simpler when you have a quadrantal angle going on there, like a point on the axis like that, negative 3, 0. Alright, so example 5, this one's really straightforward once you see it. When you don't see it, you're like, I got no clue what's going on. So pay attention real quick to this as we first off, we see all we're given is an R value, what R equals, and that's why this at first looks like total curveball. But if we just do a little bit of math real quick, we can see that if we took our equation, R equals 4 secant theta, and let's go ahead and try to get rid of this, divide both sides by secant theta. Well, R divided by secant theta, secant's 1 over cosine, so if we divide by secant, that's the same as multiplying by cosine, so R cosine theta equals 4. Well, R cosine theta, in terms of our equations, is the x coordinate, so this equation simply becomes x equals 4, which is simply a vertical line at 4. I kind of missed 4, but you get the gist. That's all there is to that problem. Okay, converting from rectangular to polar again, but this time a little bit more of a complicated equation. We've got x minus 3 squared plus y minus 2 squared equals 13, and we're trying to get that into polar form. We'll just take it step by step. So we start by taking the x minus 3 squared and the y minus 2 squared, and we go ahead and FOIL those out, and that is what gives us this equation right there. We simply FOILed out the x's, FOILed out the y's, and there we go. Combining like terms, we end up with x squared plus y squared minus 6x minus 4y equals 0. By substituting r squared in place of x squared plus y squared, here we had the x squared plus y squared, and that simply becomes r squared. And then we also substitute in the r cosine theta for the x and the r sine theta for the y, and we wind up with negative 6r cosine theta minus 4r sine theta. Simply factoring out the r that is common to all three terms, and we get r minus 6 cosine theta minus 4 sine theta. Knowing that we have r times r minus 6 cosine theta minus 4 sine theta, we know that this is two terms. The term in the parentheses and the r outside of the parentheses, and the product of those two things equals 0. So either r equals 0, which is just the single point at the origin, or it's r minus 6 cosine minus 4 sine theta, and in that case 0 is on that graph as well. Therefore, we don't need to do the r equals 0. We can simply do this, and r equals 6 cosine theta plus 4 sine theta would be our solution. If we were to graph that, we can see that the graph of r equals 6 cosine theta plus 4 sine theta from 0 to 2 pi is a circle with a center at 3, 2 and a radius of root 13, which is exactly what we should have expected from the given equation, because this would have the HK center of 3, 2, and if that's the radius squared, then it would have a radius of root 13. So you can see that the circle also has that point 0, 0 that we talked about with the r equals 0, but it is more than just a single point. It should be all of this, which is why we use the r equals 6 cosine theta plus 4 sine theta as our solution. Okay, that should do it. There's one more example in the lesson, example 7, that I think you can kind of look at and guide yourself through it. It's not too bad. That's only if you have to find the distance between two polar coordinates. It's just a law of cosines problem. I think you'll be pretty A-okay. Therefore, with that said, have fun and do your homework. That's what I wanted to do. The price I pay. Have fun, everybody. I hope everything's going well. We'll see you soon.